In this module, I am going to remind you about the Markov chain Monte Carlo methods and how that need to be implemented in R through different examples, and then I'll also show you how to implement the importance sampling in R, and then finally I'll show you how to implement the expectation maximization algorithm in R, and then do a case study for a normal mixture model through R codes. And it's not all the time the available codes would be available, but we have to generate our own code to implement those algorithms. That I'll show you how to generate those codes, how to implement those algorithms in R, and then finally through the case study and through different results that we will see and how to interpret those results. That would be clear after completion of this presentation. The previous module we have learned how to generate random variables from different parametric distributions, and sometimes very complicated distributions through rejection sampling methods. That is very relevant to the Markov chain Monte Carlo methods. But in this module, in the second module, that we are going to learn about the concept of Monte Carlo methods, and related to that we will also learn another sampling method is called importance sampling, and then the expectation maximization algorithm, and one case study for expectation maximization on Gaussian mixture model. Suppose we wish to evaluate the following integration: I equals to integrate x, gx, fx, dx, where gx is complicated and unknown functions and fx is a known probability density function. This integration can be thought of as a expectation of gx, where x is a random variable from probability density gx, fx, which is known probability distribution. According to the law of large number, above expected value I, is the expectation of gx, can be estimated by a sample mean. Let x1, x2 or xn be a sequence of random numbers generated according to the unknown density fx. Then I can be approximated by 1 by n sum over j equals to 1 to n g of xj. And this is Monte Carlo integration. This is the basic concept of Monte Carlo integration. Let's start with an example, a very simple example. In this example, I am going to evaluate an integration of a function that also can be evaluated analytically by MC method over 0 to 1. See, fx is cos 50x plus sin 20x whole square. Then let assume I equals to 0 to 1 fx gx dx, where gx is U01, uniform 0-1 distribution. At h, and let's define the function h is function x, just argument is x, and that will return the value of cos 50x plus sin 20x whole square. And then if you just draw this curve, you can see the distribution of this function. This is combination of cos and sin function by curve h, x lab equals to function y lab equals to this, and L W is 2. Then this curve function can be used to draw the curve of fx function. Now we'll integrate it. For integration, just integrate function is there. Just integrate h from 0 to 1. H is the function that you are going to integrate, and 0 to 1. It will give a numerical integration, and that value is giving around 0.96509 with absolute error 1.9 into 10 to the power minus 10. Now we'll use x equals to h r uniform 10 to the power 4. So that means it will the x would be the h of x, where x follows uniform 0 1. Now estimate int equals to say cumulative sum of x by 1 to 10 to the power 4, and estimate error is square root of cumulative sum of this expression. And then we can plot the actually by this course we can plot the 95 the actual integrated value and the 95% confidence interval here by this one. I mean, you can just go through this code, might help you to understand how this plot has been generated. Now we'll see about how to use the importance sampling in R. Before that, let's get some basic idea about the importance sampling, just recalling the concept of importance sampling in the MCMC concept. Given two probability density function f and h and a function phi such that hx equals to 0 only if fx into phi x equals to 0 and such that x follows f, then theta equals to expectation of phi x is equals to actually integration over r to the power d phi x fx dx. Exist, consider a sample z1 or zn from h. Then the importance sampling estimator theta hat is is actually 1 by n j equals to 1 to n phi zz into fzz divided by hzz is an unbiased and consistent estimator of theta. If variance of theta phi z and into fz divided by hz exists, then expectation of theta hat is minus theta square is equals to variance of theta hat is equals to 1 by n variance of theta z into fz divided by hz equals to 1 by n integrate over phi square x f square x by hx dx minus 1 by n theta square. Suppose we want to use importance sampling to estimate theta equals to probability of x greater than c equals to expectation of ix greater than c for x follows normal 0 sigma square and c greater than 3 sigma. The Monte Carlo estimator theta hat is equals to 1 by n j equals to 1 to n ix greater than c equals to 1 by n that is the number is number z belongs to j belongs to 1 to n colon xj greater than 0 will be quite poor because the vast majority of the sample values is completely irrelevant. Only the very few that exceed c matters. We now use the importance sampling to see more values above c. Let assume h mu x as the normal mu sigma square, then fx is h naught x. Fx by h mu x is equals to expect e to the power mu into mu minus 2x divided by 2 sigma square. The importance sampling estimator for mu belongs to R is actually theta hat is equals to 1 by n j equals to 1 to n I indicator function I get x greater than c into e to the power mu into mu minus 2x by 2 sigma square. So first let's see how it can be implemented in R. Importance sampling for probability of x greater than c for normal 0 1 based on normal mu 1 functions. The im functions, first let define the im functions where the pass by values are mu, c, n and x, where z equals to say mu plus x greater than c into e to the power mu into mu minus 2 into mu plus x divided by 2, and then is is mean of z. The standard deviation of z by square root of n, and c equals to mu, standard deviation equals to standard deviation, estimate is is, and lower confidence interval is ls minus actually q norm 0.975, it's 1.96 actually into standard deviation, and upper confidence interval is is plus q norm 0.95 1.96 into standard deviations. So that means this function will return the mu value, the standard error, the importance sampling estimate, and its 95% confidence interval. So that's the way the function has been developed. Now let n equals to 10 to the power 7 and x is R norm n. So x is generated from standard normal distributions and c equals to 3, mu is assumed to be 0, 1, 2, 3, 3.1, 3.15, 3.2 and 4. Tab equals to null. Now we use this function for I equals to 1 to n, length of mu, tab equals to R bind tab, call the important sampling and pass mu I, then c, n and x, that just using that for loop, and that will construct the table like this. So for 8 parameters, for c equals to 3, these are the estimates. For c equals to 4.5, if I change the c to 4.5 and mu equals to this 0, 4.5, 4.6 and 4.7, then tab equals to null, then you can use the same for loop, same function, and then finally it will give you these estimates, the 4 estimates: mu, standard error, estimate, 95% confidence interval, and lower confidence interval and upper confidence interval of corresponding to 4 mu. Then in simulation of n into 10 to the power 7 samples for sigma equals to 1 and c equals to 3, we see that the mu is equivalent to 3.15, gives the best accuracy. 3 significant digits estimating probability of x greater than 3 by 0.00135, whereas only the first digit was significant for the Monte Carlo estimator. Going a bit further, for c equals to 4.5, the Monte Carlo does not find any significant digits. Important sampling still find 2 significant digits. That is, probability of x greater than 4.5 is approximately 0.5034. To plot the confidence interval as mu varies, one can use this code, say mu equals to 0 to 120 by 20 and IM save 3 equals to matrix 1 to 605 121 by 5 matrix or initialized, and then use the for loop for I equals to 1 to 121 and then fill the matrix by the important sampling results, and then finally you just plot mu for IMPS save 3 for 3rd column, 4th column, 5th column, and then lines of this, and then finally you can see this plot. That is the important sampling plot of convergence. You can easily just run one by one each line separately and see what is the change. That might help you how that code need to be generated. So you can run all the codes one by one and see what's the changes happening in the plots. So basically the plot, the first one, the plot of mu for the 3rd column. 3rd column is actually the estimate. Then the 4th column is the lower confidence interval and 5th column is the upper confidence interval. So plot, and then the other lower and upper confidence interval was plotted by lines function. And then some lines has been some lines have been generated by line function from C 3.5 to 3.15, 3.15 to 3.15, 3.14 to 3.14, C 3.16 to 3.15, and see the IMP save matrix of 64 to 4, 64 to 5, 64 to 4, 64 to 5. And this way it will give you the plot. Just run one by one. That will give what I did over here to understand how the important sampling, the sample generated. Next, we will move to the Monte Carlo optimization methods. Before Monte Carlo optimizations, we better have a good idea about the expectation maximization algorithm, the EM algorithm, and later on we will see the MCEM. But before that, I think we better recall the concept of EM algorithms. The EM algorithm is a deterministic optimization technique that takes advantage of the following representation as a g x by theta equals x given theta equals to integration z fx z given theta dz to build a sequence of easier maximization problem whose limit is the answer to the original problem, where z is a latent variable could represent as a missing component. We thus assume that we observe x1 or xn jointly distributed from gx given theta that satisfies above representation, and that we want to compute theta hat equals to, say, argument argmax L theta x equals to argmax g x given theta. This representation occurs in many statistical settings, including censoring models and mixture and latent variable models. The actual algorithm for EM that I also try to help you to recall the EM algorithms. The pick a starting value theta naught hat and then repeat the expectation step is the q theta given theta hat m x equals to actually expectation of theta hat m log L theta x z. LC theta x z, complete likelihood, where the expectation is with respect to kz theta hat m x and set m equals to 0. Then maximize q theta given theta hat m comma x in theta and take theta hat m plus 1 equals to argument argmax over theta q theta given theta hat m x, and set m equals to m plus 1 until a fixed point is reached, theta hat m plus 1 equals to theta m. That example will clear you the algorithm. I am using one example. Say let x equals to yx and y prime is y1 y2 dot ym denotes the observed data, and z prime z plus zm plus 1 zm plus 2 zn denotes the missing data. If the distribution of x minus theta correspond to normal theta 1 distribution, and the complete data likelihood is this, easily it can be shown that the complete data likelihood is the form like this. The first part is for the observed data, and second part is corresponding to the missing data, resulting in the expected complete log likelihood is q theta naught y equals to minus 1 by 2 I equals to 1 to n yi minus theta square minus 1 by 2 I equals to m plus 1 to n expectation of theta naught zi minus theta whole square, where the missing observation zi are distributed from normal theta 1 distribution truncated in A. Doing the m step and setting it equal to 0 then lead to the EM update as theta hat m. This can be shown, if you calculate then you will get this expression theta hat equals to m y bar plus n minus m e theta prime z1 divided by n, since e z1 equals to theta plus phi a minus theta by 1 minus phi a minus theta, where phi and capital Phi are the normal PDF and CDF respectively. The EM sequence is then becomes theta hat j plus 1 equals to m by n plus n minus m by n, theta hat j plus phi small phi a minus theta hat j divided by 1 minus capital Phi a minus theta hat j. So this is the expression that we are going to use to implement in our code. Say n equals to 1000 and x generated from a normal normal variate of size n from mean from normal distribution with mean 2.5 and standard deviation 1, and x the sample from 1 to n in the proportion is n into 0.1 number of samples that you have to generate is not available. So let's suppose 10%, I'm assuming here that there is a random missing, 10% random missing is there. For that, this expression is important to assign some values, randomly selected values, as not available. Now y equals to na dot omit x and m equals to length of y, and y bar is mean of y. Theta equals to r norm 1, mean equals to y bar, sd equals to sdy, a equals to 1.5, and then non-stop one variable getting and eta equals to 1. Now we'll use a while loop called while loop. While non-stop greater than 10 to the power minus 4, then theta equals to c theta comma m into y bar divided by n. This same expression that I have shown there, this expression has been written in r comment, r expression. Then eta equals to eta plus 1, and then actually every iteration, the eta would be updated, and that will give you the number of iteration at the end of the loop. And non-stop is this is the termination condition. If non-stop is absolute value difference, the difference between the current theta and the previous theta, and the print the theta of the length of theta, and that much theta you print. Then the back length of theta actually will give you the maximum, the last value of the theta, the last iteration value of the theta. So last iteration value is say 2.73. If you run that, then it will give you the EM algorithm, is one of the EM implementation of this data. That might help you to understand how the EM actually implemented in R. Now we'll move to another case study, is fitting a mixture of Gaussian to real data. The weather forecasting in Snoqualmie Falls, the data consists of daily records from the beginning of 1948 to the end of 1983 of precipitation at that fall Washington. Each row of the data file is a different years. Each column records for that day for the years, and the days as the precipitation in units 1 by 100 inch. Because of leap years, there are 366 columns, with the last column having a not available values for 3 out of 4 years. Data can be downloaded from this link, and let's look at the distribution of the amount of precipitation on the wet day. Here is the read.csv and snoqualmie.csv data that can be downloaded from there and saved in your folder, and then that can be read through read.csv data, and then the na.omit unlist and Snoqualmie, that data you omit it wherever missing is there. Then esnoq, another variable that I have created, is wherever Snoqualmie dot vector greater than 0. So wherever it is 0, esnoq will give you the Snoqualmie vector value, and the summary of that will give you the mean is minimum 1, maximum 6, median 19, mean 32.6. Give a basic idea about the distribution. If you want to draw an histogram and a density of that particular density plot, a density over the histogram you can draw, and that will give some idea about the distribution of the data that you have. So the figure shows the histogram together with the simple kernel density estimate. This suggests that the distribution is rather skewed to the right. Notice that the mean is larger than median, and the distance from first quartile to median is much smaller than that from the median to the third quintile. One way this could arise, of course, is if there are multiple types of wet days, each with a different characteristic distribution of precipitation. That means actually it's a mixture of multiple distributions. It's not a one particular distribution that you can get from there. That could be the reason for that, and we will look at this by trying to fit Gaussian mixture model with varying number of components. Here is the normal mixture EM functions that can be called from the mix tool package, and there you just pass the SNOQ data and k equals to 2, then max iteration is 100 and epsilon is 0.01, then you will get the results on the estimate of the parameter lambda, mu, sigma and log likelihood at the estimated values, this component 1 and component 2. Let's define a function plot.norm.components where you will pass the mixture then the component dot number, and then it will generate some curve actually. So just look at this curve, then code carefully, and rather you can copy and paste and plot, run it separately will give you better idea how that code has been developed. Now we can draw this. So for two components, I am using two components, this the histogram and then lines, and then is the density function, and then the two component mixture model. The two component mixture model, if you see that also actually it doesn't fit very well. Then we can calibrate this whether it is well fit or not, that the CDF of two component mixture fx is lambda 1 f1x lambda 2 f2x. Similarly k component should be I equals to 1 to n k fix and lambda I equals to 1. Let's define a following function. This function is the p norm mix. I define this function, and this function can be used here. Say distinct dot SNOQ equals to sort unique SNOQ data that we have. Then the p norm mix, pass that value, pass the arguments to the p norm mix function that I defined in earlier slide. That will give you the TC degrees of DFS, and ECDFS can be done. ECDF is that data divided into the distinct dot SNOQ, and then plot TCDF, X lab is this and Y lab is this. It will, if you see this plot, then you will see that it is clearly violating this. It is a actually the QQ plot. So QQ plot is showing CDF, that is the theoretical CDF, and another is the empirical CDF, and theoretical CDF and empirical CDF are not at all coinciding. So the two component Gaussian mixed fit is not satisfactorily observed from the plot at the left panel. One can select the number of components by cross validation method, or one can do a statistical test. For cross validation we have to calculate log likelihood. Here is for cross validation I develop a code here. First develop a log normal mixture, a D norm mixture in this function, and then develop a log likelihood dot norm mix function x mixture. If you pass the mixture, then it will give you the return of log likelihood function. So log likelihood function that is developed in the second function is the log likelihood functions. Now one can do 5-fold or 10-fold cross validation to select the components number, but just a illustration approach, we will do a simple data set splitting, where a randomly selected half of the data is used to fit the model and half to be tested. So now the data has been splitted, and this is the code you can see, and just go through the code one by one. That will give you the clear idea what I did, and then finally you will see this plot. Likelihood, the figure shows the log likelihood of different sizes of mixture models fit to a random half of the data for training and evaluating on the other half of the data for testing. The figure estimates the 9 component of Gaussian mixture. See, this is 1 2 3 4 9. See, 9 is becoming flat. After that it's flat, so we can consider 9 as the 9 component, the component size should be 9. So the 9 component Gaussian mixture model can be fit here. That is normal mix EM, that function from mix tool can be called, and just specify k equals to 9. That will fit the 9 component Gaussian mixture, and if you just plot it like previous, you will see that it gives you better fit than the 2 component model, and that can be cross validated. That if you see that it's actually the empirical CDF against theoretical CDF, when you plot for this 9 component Gaussian mixture, it's showing a straight line. That means it's a perfect fit. So let's stop here. Next we'll continue into a few more modules about Markov chain Monte Carlo methods. So we learn the concept of Monte Carlo Markov chain Monte Carlo methods, and the use of important sampling in Markov chain Monte Carlo methods, the EM algorithm, the expectation maximization algorithm, how to implement in R, and through a case study we also see how to implement, how to interpret the results that generated by the different codes that I have developed, that are user defined codes. And I guess after this you people would be quite comfortable with handle the EM algorithm and its implementation in R.